Section 4, the science test, 40 questions. There are several passages in this test. Each passage is followed by several questions. After reading a passage, choose the best answer to each question and fill in the corresponding oval on your answer document. You may refer to the passage as often as necessary. You are not permitted to use a calculator on this test. Passage 1. Finch beak depth, see Figure 1, is an inheritable trait. It can be passed from parents to offspring. Researchers studied the beak depth of two species of finches, Geospiza fortis and Geospiza fuliginosa. Both species live on island A. G. fortis alone lives on island B, and G. fuliginosa alone lives on island C. For both species, the primary food is seeds. Birds with shallower beaks can efficiently crush and eat only small seeds. Birds with deeper beaks can crush and eat both large and small seeds, but they prefer small seeds. Study 1. Researchers captured 100 G. fortis finches and 100 G. fuliginosus finches on island A. They tagged each bird, measured its beak depth, and released it. Then they calculated the percent of birds having each of the beak depths that had been measured. The researchers followed the same procedures with 100 G. fortis finches from island B and 100 G. fuliginosa finches from island C. The results of these studies are shown in Figure 2. Study 2. After completing Study 1, the researchers returned to island B each of the next 10 years from 1976 to 1985. During each visit, the researchers captured at least 50 G. fortis finches and measured their beak depths. Then, they calculated the average G. fortis beak depth for each of the 10 years. The researchers noted that during the 10-year period, 3 years were exceptionally dry and 1 year was very wet. See Figure 3. Small seeds were abundant during wet years. During dry years, all seeds are less abundant, and the average size of the available seeds is larger. Question number 1. Based on the results of Study 1, the highest percent of finches on Island B and Island C had a beak depth of A. Island B 8 millimeters, Island C 8 millimeters, B. Island B 9 millimeters, Island C 12 millimeters, C. Island B 10 millimeters, Island C 8 millimeters, D. Island B 10 milliliters, Island C 10 milliliters. Question number 2. During which of the following years were small seeds likely most abundant on Island B? F. 1977, G. 1980, H. 1982, J. 1984. Question number 3. Study 1 differed from Study 2 in which of the following ways? A. G. fortis finches were captured during Study 1 but not during Study 2. B. G. fuliginosa finches were captured during Study 1 but not during Study 2. C. The beak depth of captured birds was measured during Study 1 but not during Study 2. D. The beak depth of captured birds was measured during Study 2 but not during Study 1. 4. It is most likely that the researchers tagged the birds that they captured during Study 1 to F. Determine how beak depth was affected by rainfall on Island A. G. Determine the average age of each finch population. H. Ensure that the beak depth of each finch was measured multiple times during Study 1. J. Ensure that the beak depth of each finch was measured only once during Study 1. Question number 5. Based on the results of Study 2, would a finch with a beak depth of 9.4 millimeters or a finch with a beak depth of 9.9 millimeters more likely have had a greater chance of survival during 1977? A. A finch with a beak depth of 9.4 millimeters because, on average, the size of available seeds is larger during dry years. B. A finch with a beak depth of 9.4 millimeters because, on average, the size of available seeds is smaller during dry years. C. A finch with a beak depth of 9.9 millimeters because, on average, the size of available seeds is larger during dry years. D. a finch with a beak depth of 9.9 millimeters because, on average, the size of available seeds is smaller during dry years. Question number 6. A researcher hypothesized that there would be more variation in the beak depths measured for the G. fortis finches when they were forced to compete with another finch species for seeds. Do the results of Study 1 support this hypothesis? F. Yes. The range of beak depths measured for the G. fortis finches was greater on Island A than on Island B. G. Yes. The range of beak depths measured for G. fortis finches was greater on Island B than on Island A. H. No. The range of beak depths measured for G. fortis finches was greater on Island A than on Island B. J. No. The range of beak depths measured for G. fortis finches was greater on Island B than on Island A. Passage 2. Substances in the atmosphere, such as Cu2+, Zn2+, Cl-, and SO4 ions, are carried down to the Earth's surface by precipitation. This process is known as wet deposition. Cu2+ and Zn2+ ions are put into the atmosphere by high-temperature combustion processes. The presence of Cl- and SO4 ions in the atmosphere can be attributed to road salt dust and electrical power generation, respectively. Study 1. A rain gauge placed on the roof of a one-story building at a specific urban site was used to collect precipitation over a 12-month period. At the same time each evening, the amount of precipitation in the rain gauge was recorded, after which the collected precipitation was emptied from the gauge and stored. Assume no measurable evaporation occurred during any day. Figure 1 shows the measured monthly precipitation in centimeters. At the end of each month, all the samples collected during that month were mixed, and some of this combined sample was analyzed for the concentrations of Cu2+ and Zn2+ ions. Using this data, the monthly wet deposition of each substance in micrograms per meter squared was calculated. See Figure 2. Study 2. Another portion of the combined sample for each month was analyzed for the concentrations of Cl- and SO4 ions. Using these data, the monthly wet deposition of each substance in milliequivalents per meter squared was calculated. See Figure 3. Study 3. The annual wet deposition of Cu2+ and of Zn2+ for the 12-month period in micrograms was calculated for the urban site. The source of the Cu2+ and the Zn2+, and also for the rural sites 1 and 2, located 50 kilometers and 100 kilometers east, respectively, of the urban site. See Figure 4. Question number 7. According to Figure 1, over the 12-month period, the monthly precipitation at the urban site was maximum in February and minimum in July. According to Figures 2 and 3, the wet deposition of which ion was also maximum in February and minimum in July? A. Cu2+, B. Zn2+, C. Cl-, D. SO4 Question number 8. Based on the results of Study 1, the average monthly wet deposition for Cu2+ over the 12-month period was F. Less than 50 micrograms per meter squared. G. Between 50 micrograms per meter squared and 75 micrograms per meter squared. H. Between 75 micrograms per meter squared and 100 micrograms per meter squared. J. Greater than 100 micrograms per meter squared. 9. Is the statement the values for Cl- wet deposition were greater during the winter and early spring when road salt is typically applied, supported by the results of Study 2? A. Yes, because Cl- wet deposition values were, on average, greater from November to April than they were from May to October. B. Yes, because Cl- wet deposition values were, on average, less from November to April than they were from May to October. C. No, because CL minus wet deposition values were, on average, greater from November to April than they were from May to October. D. No, because CL minus wet deposition values were, on average, less from November to April than they were from May to October. Question number 10. Suppose there had been no precipitation during one entire month of the 12-month period. Based on the information provided during that month, there would have been F. Significant wet deposition of all four substances. G. Significant wet deposition of Cu2+ and Zn2+, but no wet deposition of Cl- and SO4 2-. H. No wet deposition of any of the four substances. J. No wet deposition of Cu2+ and Zn2+, but significant wet deposition of Cl- and SO4 2-. 11. According to Study 3, as distance from the urban site increased, the annual wet deposition A. Increased for both Cu2+ and Zn2+. B. Increased for Cu2+, but decreased for Zn2+. C. Decreased for both Cu2+ and Zn2+. D. Remained the same for both Cu2+ and Zn2+. 12. Which of the following variables was kept constant in Study 2? F. Site. G. Monthly rainfall. H. Wet deposition of Zn2+. J. Wet deposition of Cl-. Passage 3. Cloud cover is the percent of Earth's surface covered by clouds. Cloud cover may increase because of an increase in the cosmic ray flux, the number of high-energy particles from space reaching Earth per meter squared per hour. Table 1 shows how Earth's cover of low clouds, 0 kilometers to 3.2 kilometers altitude, varies with the cosmic ray flux. Figures 1 through 3 show the relative cosmic ray flux, RCRF, the percent below the flux measured on October 1, 1965, and the monthly average cover of high clouds, 6.0 kilometers to 16 kilometers altitude, and middle clouds, 3.2 kilometers to 6.0 kilometers altitude, and low clouds, respectively, from January 1980 to January 1995. Table 1, adapted from E. Palebago and C. J. Butler, The Influence of Cosmic Rays on Terrestrial Clouds and Global Warming. Figures adapted from Nigel Marsh and Henrik Svenk, Low Cloud Properties Influenced by Cosmic Rays. Question number 13. The percent of Earth's surface covered by high clouds in January 1987 was closest to which of the following? A. 13%, B. 13.5%, C. 14.0%, D. 14.5%. 14. Question 14. Based on Table 1, a cosmic ray flux of 440,000 particles per meter squared per hour would correspond to a cover of low clouds that is closest to which of the following? F. 28.7%, G. 29%, H. 29.3%, J. 29.6%. Question number 15. Is the statement, the monthly average cover of low clouds is more directly correlated with cosmic ray flux than is the monthly average cover of high clouds, consistent with figures 1 and 3? A. Yes, because the plot for the monthly average cover of low clouds more closely parallels the plot for RCRF. B. Yes, because the plot for the monthly average cover of high clouds more closely parallels the plot for RCRF. No. C. No, because the plot for the monthly average cover of low clouds more closely parallels the plot for RCRF. D. No, because the plot for the monthly average cover of high clouds more closely parallels the plot for RCRF. Question number 16. Which of the following figures best represents the monthly average cover of high, middle, and low clouds since January 1992? E, H, G, or J? Question number 17. High clouds are composed primarily of ice crystals whereas low clouds are composed primarily of water droplets. This difference is most likely because the average air temperature at altitudes from A. 0 kilometers to 3.2 kilometers is at or below 0 degrees, whereas the average temperature at altitudes from 3.2 kilometers to 6.0 kilometers is above 0 degrees Celsius. B. 0 kilometers to 3.2 kilometers is at or below 0 degrees Celsius, whereas the average air temperature at altitudes from 6.0 kilometers to 16.0 kilometers is above 0 degrees Celsius. C. 0 kilometers to 3.2 kilometers is above 0 degrees Celsius, whereas the average air temperatures at altitudes from 3.2 kilometers to 6.0 kilometers is at or below 0 degrees Celsius. D. 0 kilometers to 3.2 kilometers is above 0 degrees Celsius, whereas the average air temperature at altitudes from 6.0 kilometers to 16.0 kilometers is at or above 0 degrees Celsius. Passage 4. Acid-base titration is a technique in which precise volumes of a titrant, an acid or base solution, are added incrementally to a known volume of a sample solution, a base or an acid solution respectively. This process can be monitored by adding an acid-base indicator, a substance that changes color over a certain pH range, to the sample solution, or by measuring the sample solution's conductivity. Conductivity, measured by kilosiemens per centimeter, is a measure of substance ability to conduct electricity. 2 titration experiments were done at 25 degrees Celsius using 0.1 molar sodium hydroxide NaOH solution and either a 0.0010 molar hydrochloric acid HCl solution or a 0.0010 molar acetic acid solution, where m is moles of acid or base per liter of solution. All solutions were aqueous. An acid-base indicator solution of nitrazine yellow was also used. Nitrazine yellow is yellow if the pH is less than 6.0 or blue if the pH is greater than 7.0. Experiment 1. A drop of nitrazine yellow solution was added to a flask containing 100 milliliters of the HCl solution. A probe that measures conductivity was placed in the solution. The NaOH solution was slowly added to the HCl solution in small increments. After each addition, the HCl solution was stirred and then the solution's color and conductivity were recorded. See Figure 1. Experiment 2. Experiment 1 was repeated except that the acetic acid solution was used instead of the HCl solution. See Figure 2. Question number 18. In experiment 1, the sample solution was yellow at which of the following values for the volume of titrant added? F. 0.8 milliliters, G. 1.2 milliliters, H. 1.6 milliliters, J. 2.0 milliliters. Question number 19. In experiment 2, the sample solution was neutral at which of the following values for the volume of titrant added? A. 0.5 millimeters, B. 1.0 milliliters, C. 1.5 milliliters, D. 2.0 milliliters. In experiment 1, if 2.3 milliliters of titrant had been added to the sample solution, the conductivity would most likely have been F less than 0.8, G between 0.8 kilosiemens per centimeter and 2.3 kilosiemens per centimeter, H between 2.3 kilosiemens per centimeter and 3.8 kilosiemens per centimeter, or J greater than 3.8 kilosiemens per centimeter. Question number 21. In experiment 2, which solution was the titrant and which solution was the sample solution? A. Titrant acetic acid, sample solution NaOH. B. Titrant HCl, sample solution NaOH. C. Titrant NaOH, sample solution acetic acid. D. Titrant NaOH, sample solution HCl. Question number 22. In experiments 1 and 2, the probe that was placed in the sample solution most likely did which of the following? F. Cooled the solution to its freezing point. G. Heated the solution to its boiling point. H. Detected the concentration of nitrazine yellow in the solution. J. Passed an electrical current through a portion of the solution. Question number 23. A chemist claimed that in experiment 2, the pH of the sample solution was greater at a value of 0.2 milliliters of titrant added than at a value of 1.8 milliliters of titrant added. Do the results of experiment 2 support this claim? A. No. At a value of 0.2 milliliters of titrant added, the sample solution was yellow, and at a value of 1.8 milliliters of titrant added, the sample solution was blue. B. No. At a value of 0.2 milliliters of titrant added, the sample solution was blue, and at a value of 1.8 milliliters of titrant added, the sample solution was yellow. C. Yes. At a value of 0.2 milliliters of titrant added, the sample solution was yellow, and at a value of 1.8 milliliters of titrant added, the sample solution was blue. D. Yes. At a value of 0.2 milliliters of titrant added, the sample solution was blue, and at a value of 1.8 milliliters of titrant added, the sample solution was yellow. Passage 4. An astronomy class is given the following facts about stellar evolution. 1. A star's evolution can be divided into 3 stages: pre-main sequence, pre-MS, main sequence, MS, and post-main sequence, post-MS. 2. Gravity causes a part of a cloud of gas and dust to collapse and heat up, creating a pre-MS star. The star's hot dust and gas emit its energy. 3. A pre-MS star becomes an MS star when the star produces the majority of its energy by fusing hydrogen nuclei proteins at its center to make helium nuclei. 4. An MS star becomes a post-MS star when the star expands in volume and produces the majority of its energy by fusing hydrogen to make helium in a shell surrounding its center. 5. The more massive a star, the more rapidly the star passes through each of the 3 stages of its evolution. 2 students discuss the evolution of the Algol system. Algol A, a 3.6 solar mass MS star, Algol B, a 0.8 solar mass post-MS star, and Algol C, a 1.7 solar mass MS star. 1 solar mass equals the Sun's mass. The 3 stars orbit a mutual center of mass, with Algol A and Algol B much closer to each other and to the center of mass than to Algol C. Student 1. The 3 stars of the Algol system formed at the same time from the same cloud of gas and dust. Algol B, originally the most massive of the 3 stars, became a post-MS star and expanded in volume, while Algol A remained an MS star, because the matter in the outer parts of Algol B was more strongly attracted to Algol A than to the matter in the inner parts of Algol B. This matter flowed from Algol B to Algol A, and over time, Algol A became more massive than Algol B. Student 2. Algol B was not part of the original Algol system, Algol A and Algol C. Algol B and the original Algol system formed in different clouds of gas and dust at different times and moved in 2 different but intersecting orbits around the center of the galaxy. During a particular orbit, Algol B encountered the original Algol system at the intersection of the 2 orbits and became part of the Algol system. Algol B became a post-MS star, while Algol A and Algol C remained MS stars. Algol B never lost mass to Algol A. Algol B was always less massive than Algol A. Question number 24. Based on the students 2's discussion, Algol B is part of the present Algol system because of which of the following forces exerted on Algol B by the original Algol system? F. Electric force. G. Magnetic force. H. Gravitational force. J. Nuclear force. Question number 25. Based on students 1's discussion in Fact 4, while matter flowed between Algol A and Algol B produced the majority of its energy by fusing A. Hydrogen nuclei to make helium nuclei at its center. B. Hydrogen nuclei to make helium nuclei in a shell surrounding its center. C. Helium nuclei to make hydrogen nuclei at its center. D. helium nuclei to make hydrogen nuclei in a shell surrounding its center. Question number 26. Suppose that the chemical composition is uniform among stars formed from the same cloud of gas and dust, but that chemical composition varies among stars formed from different clouds of gas and dust. Student 2 would most likely agree with which of the following statements comparing the chemical compositions of stars in the present-day Algol system at the time they were formed. F. Algol A and Algol B had the most similar compositions. G. Algol A and Algol C had the most similar compositions. H. Algol B and Algol C had the most similar compositions. J. Algol A, Algol B, and Algol C had the same composition. Question number 27. If the mass of the Sun is 2.0 times 10 to the 30 kilograms, what is the mass of Algol C? A. 1.6 times 10 to the 30 kilograms. B. 2.0 times 10 to the 30 kilograms. C. 3.4 times 10 to the 30 kilograms. D. 7.2 times 10 to the 30 kilograms. Number 28. Which of the following statements best explains why the reaction described in Fact 3 requires a high temperature and pressure? F. All protons are positively charged and like charges attract each other. G. All protons are positively charged and like charges repel each other. H. All electrons are negatively charged and like charges attract each other. J. All electrons are positively charged and like charges repel each other. Question number 29. Based on Fact 5 and Student 1's discussion, which of the following 3 stars in the Algol system, if any, was most likely the first to become an MS star? A. Algol A, B. Algol B, C. Algol C, D. The 3 stars became MS stars at the same time. Question number 30. Based on Fact 5, would Student 2 agree that by the time Algol A stops being an MS star, Algol A will have spent as much time being an MS star as Algol B spent being an MS star? F. Yes, because according to Student 2, Algol A has always been more massive than Algol B. G. Yes, because according to Student 2, Algol A has always been less massive than Algol B. H. No, because according to Student 2, Algol A has always been more massive than Algol B. J. No, because according to Student 2, Algol A has always been less massive than Algol B. Passage number 6. 3 experiments were done using CO2 krypton, or O2. For each gas, 1. A 3-liter steel vessel was fitted with a cap that contained a gas inlet valve and a pressure and a temperature sensor. 2. Air was pumped out of the vessel until pressure measured 0.00 torrs. 3. The vessel was placed on a balance and the balance was reset to 0.00 grams. 4. Some of the gas was added to the vessel. 5. When the gas in the vessel reached room temperature, 22 degrees Celsius, mass and pressure were recorded. 6. Step 4 and 5 were repeated several times. These experiments were then repeated, except that a 6-liter vessel was used. See Figures 1 and 2. Question number 31. Based on Figure 2, if 13 grams of krypton, Kr, had been added to the 6-liter vessel, the pressure would have been A. Less than 200 torr, B. Between 200 torr and 400 torr, C. Between 400 torr and 600 torr. Question number 32. Suppose the experiments had been repeated except with a 5-liter vessel. Based on Figures 1 and 2, the pressure exerted by 7 grams of CO2 would most likely have been F. Less than 500 torr, G. Between 500 torr and 1,000 torr, H. Between 1,000 torr and 1,500 torr, J. Greater than 1,500 torr. Question number 33. Based on Figures 1 and 2, for a given mass of O2 at 22 degrees Celsius, how does the pressure exerted by O2 in a 6-liter vessel compare to the pressure exerted by O2 in a 3-liter vessel? In a 6-liter vessel, the O2 pressure will be A. Half as great as in the 3-liter vessel, B. The same as in a 3-liter vessel, C. 2 times as great as in the 3-liter vessel, D. 4 times as great as in the 3-liter vessel. Question number 34. Which of the following best explains why equal masses of O2 and CO2 at the same temperature and in the same size vessel had different pressures? The pressure exerted by the O2 was F, less, because there were fewer O2 molecules per gram than there were for CO2 molecules per gram. G, less, because there were more O2 molecules per gram than there were CO2 molecules per gram. H, greater, because there were fewer O2 molecules per gram than there were CO2 molecules per gram. J, greater, because there were more O2 molecules per gram than there were CO2 molecules per gram. Question number 35. Suppose the experiment involving O2 and the 6-liter vessel had been repeated, except that at a room temperature of 14 degrees Celsius. For a given mass of O2 compared to the pressure measured in the original experiment, the pressure measured at 14 degrees Celsius would have been A, less, because the pressure is directly proportional to temperature. B, less, because pressure is inversely proportional to temperature. C, greater, because pressure is directly proportional to temperature. D, greater, because pressure is inversely proportional to temperature. Passage number 7. The human threshold of hearing is a minimum intensity at each sound frequency required for a sound to be heard by humans. The human threshold of pain is the maximum intensity at each sound frequency that humans can tolerate without pain. The figure below displays the sounds in water and in air, the human thresholds for hearing and of pain. The figure also shows S, the percent increase in air density and water density that accompanies the compression of air and water by sound waves of given intensities. Sound intensities are given in decibels, dB, and frequencies are given in hertz, Hz. 1 hertz equals 1 cycle per second. Question number 36. According to the figure, which of the following is closest to the lowest frequency that can be heard by a human being? F, 8 hertz. G, 20 hertz. H, 1000 hertz. J, 20,000 hertz. Question number 37. As humans age, it is common for selective hearing loss to occur at high sound frequencies. Which of the following figures best illustrates this loss? A, B, C, or D? Question number 38. Based on the figure, a sound of a given frequency will have the highest intensity for which of the following sets of conditions? F, sound is passing through water. S is 100%. G, sound is passing through water. S is 10 to the negative 8%. H, sound is passing through air. S is 100%. J, sound is passing through air. S is 10 to the negative 8%. Question number 39. A student hypothesized that sounds of any intensity at a frequency of 10 to the 5th hertz would be painful for humans to hear. Do the data in the figure support this hypothesis? A, yes, because the threshold of pain is relatively constant with changes in frequency. B, yes, because as frequency increases above 10 to the 5th hertz, the threshold of pain increases. C, no, because humans cannot hear sounds at 10 to the 5th hertz. D, no, because the threshold of pain is relatively constant with changes in frequency. Question number 40. Based on the figure, does S depend on the frequency of a sound wave of a given intensity? F, yes, because as frequency increases, S increases. G, yes, because as frequency increases, S remains constant. H, no, because as frequency increases, S increases. J, no, because as frequency increases, S remains constant. This is the end of test 4. Stop. Do not return to any other test. You may go back and continue to work on this test.